the eigenfunctions the eigenfunctions of a Hermitian operator are orthogonal to each other as long as the eigenvalue is non-degenerate. We'll talk about that in a second. But the most important part is that they are orthogonal, and even if the eigenvalues are degenerate, we can make a set of eigenfunctions for that operator that are all mutually orthogonal. So what does it mean to be orthogonal? We talked about this in class last week, right? That we were sort of generalizing the dot product to something called the inner product. Two functions. God, you guys can still hear me, right? Okay, I have a cold, that's why I had this on, but that's getting really annoying. Two functions, f and g, are orthogonal if the integral over all space of the complex conjugate of f times g is equal to 0. Right? That defines function orthogonality. Another way, a conceptual way of saying that is that if you take functions f and g, in some mathematical sense, they don't overlap with each other. And that's a bit of a weird statement that we're going to talk about more when we have more specific examples. Okay. Two functions are orthogonal if the integral over all space of s star times g is equal to 0. Alright, so let's actually show that Hermitian operators have orthogonal eigenfunctions. Let's consider some general operator O. We know with an eigenvalue equation, O operating on its eigenfunction gives an eigenvalue times the eigenfunction. And we're going to say that O is Hermitian. So let's look at two different eigenfunctions. O operating on f sub m. So now we have two eigenfunctions, f sub m and f sub n. And their eigenvalues are different. If they were the same, we would say they were degenerate. If they're different, they are not. Okay. Alright, and what we want to do is look at the integral over all space of eigenfunction f sub n star times the operator acting on eigenfunction f sub m. Okay. And by definition, that just gives us the eigenvalue times the eigenfunction. Now let's take a look at this equation and let's evaluate it differently. Because this operator is Hermitian, the following must be true. Right? I can pull the operator over to the left, take the complex conjugate of the whole thing, and then integrate. Right? That's just the definition of it being Hermitian. And then this becomes integral over all space lambda n f sub n star f sub n. So all we did here was we take O operating on the eigenfunction, we pull out the eigenvalue times the eigenfunction. Okay. And now we can subtract these two functions. We can subtract these two different equations from each other. And when we do that, what we get is lambda n minus lambda m times f sub n star f sub m is equal to 0, right? These two things started as the same equation, so when we subtract them, they have to be equal to 0. So we already know that this is not equal to 0, right? The two eigenvalues are different. So therefore, the integral over all space of the two eigenfunctions has to be equal to 0. This proof doesn't work if the two eigenvalues are the same, if it's degenerate. But even if it is degenerate, we can make a set of eigenfunctions where each eigenfunction is orthogonal to every other eigenfunction of the operator.